So, without further ado, let's get started. This is TensorFlow Lite Week 1. During this first week, we'll first talk about the early approaches for machine learning at the edge and the challenges we face when we try to embed deep learning models in edge devices. Then, you'll learn about TensorFlow Lite, its goal, advantages, and architecture. Next, we work on our first hands-on project throughout this course, which is an Android app for recognizing dogs and pictures taken with a camera and using a machine learning model optimized with tflite. Finally, we'll reveal all of the content seen throughout this first week. When we talk about artificial intelligence today, especially machine learning, most of the time we mean deep learning models. That's because during the past decade, deep learning has emerged as the most successful machine learning approach for problems related to artificial intelligence. Among the main reasons, there's the ability of those models to learn how to make predictions and at the same time how to represent features from samples presented as input. That makes deep learning models flexible because they can be applied to problems from many different domains with just a few or sometimes almost none changes. That's something classical machine learning models couldn't do by themselves. Before the breakthrough of deep learning, most machine learning models were designed based on handcrafted features. Their representations were designed by specialists, so those models were very problem-dependent. That scenario influenced how classical machine learning models were embedded in edge devices. Since their features were handcrafted and they were very problem-dependent, they could be designed so their complexity could fit the target device and the problem at hand. One of the best examples of that approach is the famous face detection algorithm proposed by Viola-Jones in 2001. That algorithm was the pioneer of face detection in real time, and it was so successful that the autofocus feature available in most cameras at the time used to run that method. Its principle is very simple. It splits the input image into grids and applies a face detector in each of those grids. Since finding a face in a grid is a rare event, the method applies a cascade of weak classifiers, which are trained to predict if there are no faces in a particular grid. If the confidence of the first classifier is too low, then the method runs the second. The same process is applied throughout the entire cascade. If the confidence of the last classifier is also low, the method assumes there is a face in that particular grid. Note, the key point for high performance is the fact that the cascade should finish as soon as the method is confident enough there are no faces in that particular grid. Also, since finding a face in an image is a rare event, most of the cascades will be short, which helps the method reach real time. A second point here is the features the method considers. They are hard features, which are well suited for face detection, since they can represent well the color contrast between the regions of both eyes and nose, and both eyes and mouth. Also, they are very simple, so the computational cost to apply them is low, especially when compared to more sophisticated methods. Although Viola-Jones face detector was successful, it presents a lot of limitations related to adapting the method to other problems, such as head detection or person detection. That's because hard features do not represent well textures and shapes. Also, the original method assumes the target object, originally a face, is a rare event, so the method does not suit well for detecting objects usually more present and images, such as trees in a forest or cars on the road. Fortunately, in 2012, the world was presented to the first successful application of a deep learning model in a famous benchmark competition of image classification. Although the fundamental concepts of deep learning were established decades ago, that was the first successful demonstration of its power. As already mentioned, deep learning models can learn how to represent features, which makes them very powerful and flexible to solve different problems. With so many advantages, deep learning overcame Viola-Jones face detector and now represents the state-of-the-art in face detection and many other problems related to computer vision and other fields, such as speech processing and natural language processing, to name a few. However, deep learning models are very big. It's not uncommon to see DL models with more than 1 million parameters. That means they are computationally expensive and they need powerful machines to run in a reasonable amount of time. Because of their large size and expensive computational cost, running deep learning models in edge devices represents a serious challenge. As already mentioned, one classical approach to overcome that challenge is to run the model in an external machine, which is supposed to have more computational power. In general, that means a large server with many GPUs and a lot of RAM available. The edge device would have access to the model via a web API, which allows its clients to send the input data to the model and collect its predictions as a response. That cloud-based approach is valid and has been used by many successful commercial applications. However, it also presents some issues that can limit the development of mobile apps. The first and most obvious one is the need for an internet connection. Since the model is not stored inside the edge device, a connection to an external machine that actually stores the model is needed. That means if that connection is lost for some reason, like a low signal or network stability, the application automatically loses its machine learning capabilities. The second issue of that cloud-based approach is the battery draining caused by the need of keeping a connection to an external machine. As we know, Wi-Fi antennas and sensors are one of the most battery draining components of smartphones, so depending on their use to have continuous access to an external machine learning model is guaranteed to consume the device's whole battery in a short time frame. Finally, the third main issue of that approach is the delay related to the time the device request takes to reach the server, how long the server takes to run the model, and the time the server's response takes to reach back at the device. All of that communication is also exposed to connection instability, which may increase the delay. In summary, that scenario can damage the user's experience, especially if the mobile app is supposed to run in real time. Because of the issues faced by cloud-based approaches, many frameworks for deep learning models at the edge have been developed recently. The most famous are TensorFlow Lite by Google and PyTorch Mobile by Facebook. The goal of both frameworks is to allow mobile applications to efficiently run deep learning models 100% entirely in the edge device. To do that, those frameworks provide many optimization features we are going to discuss later throughout this course. Once again, it's worth mentioning, during this course, we will focus on TensorFlow Lite. However, both frameworks have the same principles, so all of the content presented during this course can be easily transferred to PyTorch Mobile.